Welcome back. We're going to continue with our trigonometry unit in section 13.2. We're going to finish this section up today. Our targets are the following. I can convert between radian and degree angle measures, find the arc length and sector area with the given radius and central angle, and evaluate the 6 trig functions given a radian angle. We're also going to fill in your unit circles, so hopefully you got one of those in class today. If not, you can go to my website, and in the trigonometry in chapter 13 and or 14, there should be links where you can go print off a unit circle. So have those things ready for tomorrow in class. Okay, so here are some formulas that you're going to want to have in your notes. Arc length of a sector, area of a sector. Arc length, S equals R times theta, or where the radius, R is a radius and theta is the angle in radians. And area of a sector, 1/2 R squared times theta, R is the radius and theta is the angle in radians. So notice that the angle has to be in radians. I'm giving you an angle in degrees, you have to convert it first. Arc length, the S, that deals with kind of the length of, if you think about this, the crust. If you think of this as a piece of pie or a piece of pizza, it's the crust. The area then, that would be how much toppings, how much crust you place on top. That's what the area is. Okay, it's all the stuff covering that piece of pizza, that piece of pie. Okay. Make sure you have those formulas down in your notes, please. Let's look at this. Find the arc length and area of the sector with R 15 and theta 60 degrees. First thing we have to do is we have to convert degrees to radians. So you can multiply by pi over 180 or set up a proportion like I did here. Either way you solve, 60 times pi over 180, if you look at it in blue, is 60 pi over 180 or pi over 3. However you want to do it. So now we just plug pi over 3 in for theta into both formulas. The radius is 15. 15 times pi over 3 is 5 pi, or 15.7 units. That's the length. Area 1/2 R squared times theta. Plug that in, 1/2 15 squared times pi over 3, 37.5 pi, or 117.8 square units. So that's a real quick example of arc length and area. Okay. We'll get more examples of area and arc length in class tomorrow. Keep that example you had previously, or the previous slide I should say, for tomorrow. We're going to skip ahead to special triangles. Let's look at 45. We kind of discussed this already a little bit. Let's look at 45, 45, 90 triangles. I have a triangle with two 45-degree angles, then I have an right angle, obviously. Then, if I remember right, my base sides are 1. My hypotenuse is, I should say my legs are 1. My hypotenuse is square root of 2. Okay, so in this first, we call this a 45, 45, 90 degree triangle. So let's find the 6 trig functions here. Sine of 45, cosine of 45, tangent of 45, and cosecant 45, secant of 45, and cotangent of 45. Obviously degrees for all these. What are these ratios going to be? Well, the sine of 45 degrees, doesn't matter what I'm saying, let's say I'm in this corner, okay? Sine is opposite over hypotenuse. 1 over the square root of 2, which by now we know that that is just the square root of 2 over 2. Okay? Now if we look at cosecant, now that's a flip. If I look at that, cosecant, instead of opposite over hypotenuse, would be hypotenuse over opposite, or square root of 2 over 1, or just square root of 2. Cosines, let's spread these out a little bit here. Can't do that. Give us a little bit over anyway. The rest of these. Okay. Cosine 45 degrees, cosine So got all off. Adjacent over hypotenuse. That is 1 over the square root of 2 as well, which we just proved is the square root of 2 over 2. So that's square root of 2. And for secant, it would be square root of 2 as well. Square root of 2 over 1 or square root of 2. In fact, you're saying they're never the same. Sine and cosine and cosecant and secant are never the same. This is the only value that this happens. This is kind of the tipping point where they oscillate between values. This is the tipping point where the cosine and sine are equal. It's 45-degree angles. A tangent of 45, well, opposite over adjacent, that's 1 over 1, which is just 1. If we flip that for cotangent, still 1 over 1 over 1. So those are the special values for 45-degree angles for sine, cosine, tangent, and their reciprocal function. Excuse me, their inverse functions, cosecant, secant, and cotangent. Okay, so now let's look at the other special triangle, 30, 60, 90-degree triangle. So put the 30 down here, 60 up here, and the 90-degree at the bottom. Remember, the cross from 30 is 1, hypotenuse is 2, and then the square root of 3 is the other leg. So let's look at these values. And we'll just do the sine, cosine, and tangent for these, because we can obviously flip them and find the other values. Sine of 60, cosine of 60, and tangent 60. If you want to find cotangent, secant, and cosecant, you can do that as well for each of these. And over in this box, we're going to put 30-degree angles, sine, cosine, and tangent. So, 60-degree angles. Sine is opposite over hypotenuse. That's square root of 3 over 2. Nothing to simplify there. Cosine of 60, adjacent over hypotenuse. That's 1 over 2. And the tangent of 60 is the square root of 3 over 1, or just the square root of 3. Square root of 3 over 1, or just the square root. Sine of 30, that's opposite over hypotenuse. We get 1 over 2. Cosine of 30 is adjacent over hypotenuse, which is square root of 3 over 2. It's familiar, doesn't it? And tangent 30 would be opposite over adjacent, 1 over the square root of 3, which comes out to be the square root of 3 over 3. So if we notice, like I was talking before, the oscillating point, sine of 60 is the same as cosine of 30. Cosine of 60 is the same as sine of 30. They oscillate back and forth. We're going to graph these in chapter 14, and you'll see a little bit more visually what I'm talking about right here. So, as you can see, we don't really need this table to necessarily find all of our trig function values for our special angles, 30, 60, and 45. We can just draw the triangles and we can write out the ratios. 45-degree angle sine, opposite over hypotenuse. We know that's 1 over the square root of 2, or square root of 2 over 2. And we can do that for the rest of them. Now, cotangent and pi over 3. Well, cotangent is the reciprocal of tangent. And plus, what's pi over 3? The pi over 3 is the same as a 60-degree angle, if you don't believe me. Pi over 3 times 180 over pi. So we convert from radians to degrees. For 180 over 3, which is 60. So the cotangent of 60, well, that's like what's in the table. That's square root of 3 over 3. That's reciprocal of tangent of 30, which is the square root of 3, or excuse me, tangent of 60. So we can use these ratios, these special triangles, and we can find these ratios without memorizing the table. One last thing before we finish up for today is a unit circle. You should have a blank one. We're going to talk about, I'm going to show you a filled in one here in a minute. You should have a blank one that looks something like this. We're going to fill it in here, and I want you to copy that down. We're going to discuss where these angles come from. Okay, here is a unit circle. Unit circle is a very nice little tool that can help us find many trig function values going all the way around our unit circle. Okay? As you can see here, we have the 30, 45, and 60-degree angles right here in quadrant 1, because that's where they would be drawn if we drew them in standard plate or form. Initial side on the x-axis, terminal side with around the unit circle. These end in quadrant 1. And notice we have the radian values as well. So let's create a quick conversion. And we have some x and y coordinates. Okay? Some x and y coordinates as we go. Those x and y coordinates, they actually are very important to us because they actually represent the cosine and sine function. The x-coordinate is the cosine of theta. The y-coordinate is the sine of theta. So all the way around the unit circle, we're directly given sine and cosine. And then if we really want to get the inverse, we know that secant is the reciprocal of cosine, or 1 over cosine. Sine is the reciprocal of cosecant, 1 over sine. And tangent, we're going to learn eventually, but I'll give you this information now. Tangent is sine over cosine. So we can get all those ratios all the way around the unit circle. If you look, why does it work out? And a lot of the values seem to repeat, right? It's 1/2, but maybe it's negative. Well, it's negative because we go left of the y-axis over here at 120. Okay, if I'm looking at this coordinate here, negative 1/2 and square root 3 over 2. They look to be mirror images of each other. They're the same values as one's negative, one's positive. Well, we're in quadrant 2. The x-coordinate is negative in quadrant 2. So that's why it's that way. But why is it the same value? Well, let's look at the angle. This is a 60-degree angle, right? I draw this in. Oops, let's get it straight. Draw this in. Here's our 60-degree angle. Okay, if I take and I flip that angle, if I flip that angle and I reflect it, it lines right up on that spot. So it's basically, I've reflected the 60-degree angle over the y-axis. That's why the coordinates are very similar. That's why 120 degrees is very similar to a 60-degree angle in value. Okay? And if you go down below the x-axis, we go down below, I had to draw that. If we go down below the x-axis, we can see that at 300, we also get similar values to 60 degrees. Well, if I draw in an angle here, it's like a negative 60-degree angle, isn't it? It's the same thing from 300 to 360. Down over here, we have 240. Has a very similar values. They're both negative because they're in quadrant 3. But that's why all around the unit circles, these values keep popping up, because they're just reusing some of the other angle values. It's just for in different quadrants. So we're talking about these things called reference angles eventually in this unit. And those angles are really what they're showing is these angles all have reference angles of 60 degrees. Okay, but copy these values down in the unit circle. It's going to be very, very helpful to you as we go forward. So have your own copy of this. Okay, embeddedmath.com. You can print out a blank one, print out a filled-in one. It's how you use it, whether you have to have it memorized or not, is not my main concern. Okay, I think we hit these top two targets pretty well. Convert between radians and degree angle measures. Okay, we found the arc length in the area sector with the given radius and central angle. We also added to that, we did some unit circle stuff, and we showed how those special angle values showed up on our unit circle. We're going to use that more in future lessons, so more today was just to expose it and have it in our possession so we can use it later. Please bring your notes with you. We'll be ready to go to tomorrow class.